solutions. We're going to get into some density questions now. Previously, we've only been doing some mole questions and some questions involving molar mass. All right, so we're on to question 13 here. And question 13 says, okay, we've got ice cream that has a density of 548 grams for every liter of ice cream. And what do we require? Oh, so we're also given that we have an ice cream cone. If an ice cream cone is 220 grams, maybe? And I think we can presume that's the ice cream part, not the cone part. So we have 220 grams, and the question asks, what is its volume in mils? All right. So what should we begin with here in a density question? Okay. Well, we're going to choose the value that is specific to our situation. Now, the density of ice cream is a constant value that's true for all ice creams, including this one. So this is our most specific value that pertains to our question. So we're going to start with our 220 grams, and we're going to try and convert that into volume. So we're going to use density because on the front page we can see that density allows us to convert mass to volume or volume to mass. All right. So I'll multiply by my density quantity here, but I want my grams on the bottom so they cancel out. That means I've got 548 grams of ice cream for every 1 liter of ice cream. However, I'm asked to give the volume in mils, so I should probably do one more step where I convert liters into milliliters. And I know that 1,000 milliliters is in my Nalgene water bottle of 1 liter. That helped me remember. So liters cancel out, grams cancel out, and then we can just punch into a calculator. 220 plus nothing times 1,000 divided by 548. And that gives us a value of 401 milliliters of ice cream. How many sig figs should I have? Looks like only 2. So I'll call that 4.0 times 10 to the 2 milliliters of ice cream. Okay. So let's move on to question 14. So that's about the largest sapphire ever mined. And that was mined this year, in the beginning of the year. I think it was January. And now sapphire is actually just aluminum oxide in the same way that carbon can be found in different forms, including diamond or graphite or graphene or buckyballs. Aluminum oxide can also be found and compressed into a gemstone, similar to the way diamond is. Similar to the way carbon forms in diamond. All right, anyways, that's enough of that. What are we given? So we know that sapphire is aluminum oxide. That might come in handy. And it has a density of 3.98 grams for every mil, so pretty dense, about 4 times denser than water. All right, and the largest sapphire ever found, mined this year, has a volume of 70 milliliters. All right, so can I picture that? How big is a milliliter? Well, I know a can of Coke is about 355 milliliters. So that's about a fifth of the volume in a can of Coke, so pretty big. And the question is, how many oxygen atoms are there? All right. So what's specific to this specific sapphire? Well, it's not the density. Density is a general principle for all sapphires, generally. There's probably a little bit of variation within them. But this specific sapphire is quite big. It has a volume of 70 mils, and so that's what we're going to start. 70 milliliters. And then we got to convert that. Well, we need to turn into atoms. Can I convert the number of liters into a number of atoms somehow? Well, let's take a look at our conversion factors. Is there something that converts volume into atoms directly? And it doesn't look like it. Moles into volume, if we're talking, this is for solutions, of course. Moles into volume if we're talking about gases. So the only other volume quantity that we can convert is density, because we're not talking about a solution, and we're not talking about a gas at standard temperature and pressure. So our only possible conversion factor left is density. Okay. So we're going to use the density to convert our volume into something else. In this case, just grams. And maybe grams will allow us to be a little more flexible. All right, so let's try it. So I want to get rid of my mils. So I'm going to put the mils on the bottom here. And I'm going to cancel out, pardon me, I'm going to put grams on the top. So 3.98 grams. And that cancels out my units of volume. Now I have a mass. I'll be able to find the mass of that sapphire. All right, that's fine. But we weren't asked for the mass. We're asked for the number of oxygen atoms. Okay. Well, I'm not sure how to do that yet, but I know in general that it's helpful to find the number of moles if I'm stuck. Can I turn mass into a number of moles? And mass into moles quantity. A molar mass will help us with that. But to do that, we've got to find the molar mass of aluminum oxide. So to do that, we've got 2 aluminums, which is 2 times, what's the molar mass of aluminum? 27.0. 27.0 grams per mole. And 3 oxygens, well, we've seen that one before. It's 3 times 16.0 grams per mole. And when we add that together, 2 times 27 plus 3 times 16, I get 102 grams per mole for, actually it's 102.0. We'll see if that matters for sig figs later. Grams per mole. Okay. So then I can convert my number of grams in my sapphire to a number of moles in my sapphire. My grams cancel out, so I can put my 102.0 on the bottom, and I convert it into moles. My grams cancel out. Now I have a number of moles, but I want the number of oxygen atoms. So to do that, I should probably convert the number of moles into the number of aluminum oxide molecules. Okay, so I can say 1 mole is equal to 6.02 times 10 to the 23 Al2O3 molecules. Moles cancel out. And then I can say there are 3 oxygen atoms for every 1 aluminum oxide molecule. 1 Al2O3 molecule is equivalent to 3 atoms of oxygen. Okay. We can just finish that off by saying, okay, 70 times 3.98. I'll just multiply the tops across times 6.02 times 10 to the 23 times 3, and divide that all by 102, and I get some number of atoms. How many sig figs? Well, it's about 70 mils, but that's not a very precise value, I bet. I bet they didn't figure that out by difference or anything like that. So I assume there's only 1 sig fig here. So that means 1 sig fig in this answer. And that gives us 5 times 10 to the 24 oxygen atoms in the largest sapphire, which has a name, but I forget it. All right, let's move on. The density of air near sea level is about 1.23 grams for every liter of air. That's about true. All right. And room 308 has a volume of about 6.00 times 10 to the 20, pardon me, times 10 to the 4 liters. And I didn't measure that. I reasoned it when I was at home, but I think it's somewhere in the ballpark. So we can find a ballpark value for the weight of air in room 308. Oh, and so we want what is the weight, or in other words, what is the mass of the air? Okay, so let's start with I guess we should start with the volume, 6.00 times 10 to the 4 liters. And if we wanted the weight of the air, we can really just convert that quite simply into using our density quantity. It converts liters into mass. And so I can say this for every 1 liter. You can find out the mass. 6 times 10 to the 4 times 1.23. That gives us 73,800 grams of air, or about 73 kilograms, 0.8 kilograms of air. Interesting. Okay, that was pretty simple. Moving on, so we've got the International Space Station, and it is pressurized, has a volume of 932,000 liters. And what do we know? We know that we want to fill it with nitrous oxide. We're not sure if nitrous oxide, the molecular composition, is going to be important or not, but we do know that it's at STP, and that's going to be important. And we want to know how many moles of laughing gas would be needed to fill the International Space Station. All right. So let's begin. We're going to begin with the volume, I suppose. That's the only thing we're really given to start, so we know that there's 932,000 liters. And I need to turn that into a number of moles of gas at STP. Now, the term STP, jumps out at me. That makes me think that I'm going to end up using my molar volume. I'm going to convert between moles and volume. Every gas at standard temperature and pressure, meaning 0 degrees Celsius and 1 atmosphere of pressure, well, they all occupy about 22.4 liters of space, or 22 nulgens of gas. All right, so that's actually pretty easy. I can say, okay, I want liters to cancel out. So I'll use this conversion factor here, where liters are on the bottom. I get 22.4 liters for every 1 mole. And that will tell me how many moles of laughing gas I would need. Liters cancel out, and I just have moles as my unit. So that means I can just type that in. So I got 932,000 divided by 22.4. All right. And so I get, how many sig figs should I have here? Well, that's about 3 sig figs, which is pretty precise. I got 3 sig figs for the molar volume as well. So I should have 3 sig figs here. So I've got 4.16 times 10 to the power of 4 times 10 to the power of 4 moles of NO2. All right. Moving on. All right, so for question 17, we've got Pip inhaling 4.2 times 10 to the 21 helium atoms. And the question is, well, what volume of a cloud would this cloud of helium occupy at STP? Okay, so we're going to turn atoms into a volume. 4.2 times 10 to the 21 atoms. Now, STP, again, we want to be thinking probably about our molar volume, which converts volume. Every gas at STP occupies 22.4 liters of space. But we don't know how many moles of atoms this is yet, so maybe we should start by turning that into a number of moles. So if I want to turn that into 1 mole, Well, how many atoms are in a mole? Well, there's 6.02 times 10 to the 23 atoms in a mole of atoms of helium or of anything else. And then maybe I can convert moles directly into liters, because when we have a gas at standard temperature and pressure. So that means I'll have 22.4 liters for every 1 mole of helium. Moles cancel out, atoms cancel out, and that's something we can just punch into a calculator. So I've got 4.2 times 10 to the 21 times 22.4 divided by 6.02 times 10 to the 23. And I get about a little, like 150 liters, say, or milliliters, say. How many sig figs? 2 sig figs? So let's say 0.16 liters of helium. Okay. So moving on. Question 18 says, it's recommended that you add 12.0 milligrams of bromide for every liter of water in a hot tub. The question is, what's the molarity of a well-kept hot tub? So, okay, so what is molarity anyway? What's the molarity? Well, molarity means to express a concentration, and to express that concentration in terms of moles per liter. Okay, so for number 18, so molarity, so that's a concentration, expressed in moles per over liters. Okay, so if I can find out how many moles I have for every liter of water, how many moles of bromide, well, I should be able to figure out what the concentration is. So what do I have here? I have 12 milligrams of bromide for every liter. So if I can figure out how many moles of bromide that is, I should be good. Okay, so I've got 12.0 milligrams of bromide. And, well, first I should probably turn that into grams. So I know that's 1 gram is 1,000 milligrams. Milligrams cancel. Okay. And I need to know the number of moles. So I can convert that using a molar mass. Now the molar mass of bromide, well, what's bromine? Bromine has a molar mass of 79.9. Bromide is 2 of those. 2 times 79.9, which is 159.8, which is actually too many sig figs, but I'm going to keep it because abbreviating it would be a hassle. Okay. All right, I'll deal with the sig figs later. It's 159.8 grams for every 1 mole. Now my grams cancel out as well. That'll tell me how many moles I have. Okay, so let's just find out. So I have 12 times divided by 1,000 divided by 159.8. That'll give me 7.5, so not very many moles, 7.5 times 10 to the negative 5 moles. And if we look back at the question, that says for every liter. So that's how many moles are in a liter. There are this many moles in a liter. So the molarity is just 7.5 times 10 to the negative 5 moles for every 1 liter, which is 7.5 times 10 to the negative 5 molar, or moles per liter. All right. making some progress here. Let's move on to question 19. All right, so what's the molarity of a solution? So that's what we're asked for. What's the molarity of a solution that is made by dissolving 20 grams of, what is that, phosphoric acid, I think? I haven't thought about naming acids in a while. I think that's what it's called. And we have some volume. All right, so kind of like this one, we need to know a certain number of moles and a certain volume. And then we should express a molarity. Okay. So I'm going to write down those quantities. No, 19. Just 19. All right. Express it like this. I can see the question, hopefully. And also my workspace. All right. So in order to find the molarity, I need to find the moles. I need to divide it by the liters. So let's start out by finding the moles. Okay, so I have 20.0 grams of H3PO4. And okay, so I can convert that into moles using molar mass. So what's the molar mass of H3PO4? Well, I got 3 times 1.0 for hydrogen. I've got 1 phosphorus. What's the molar mass of phosphorus? It's 31.0. So it's 1 times 31.0 for phosphorus. And I have 4 oxygen, so 4/16. So that's going to give me 3 plus 31 plus 4 times 16, which is 98 grams per mole. All right, so if I have 20.0 grams, I can say, well, I know that 98 grams is 1 mole. So 20 grams, I'm just going to say is about 1/5 of a mole, or 0.2. Let's find out exactly how many. 20 divided by 98, but I already have 98 in my calculator, so I'm just going to press the answer button, cheekily. Oops, glare. And I get 0.204, which is about 0.2. Not bad. I should actually keep 3 sig figs, because that should have been 98.0. So I'll call that 0.204 moles. And if I want to find the molarity, I can divide that by the number of liters. And the number of liters, well, I have 50 mils. So I can convert 50 mils into liters by saying 1 liter is 1,000 mils. I can see I divide 50 by 1,000. And I get 0.0500 liters. And so the molarity is going to be 0.204 moles over 0.0500 liters. All right, so 0.204 divided by 0.05, and I get about 4.08 molar. All right. So on to question 20. All right, so Maya needs to make a 0.300 liter solution. And that solution has to have a certain concentration, and it contains silver nitrate. And we're asked, okay, well, what is the mass of silver nitrate she needs to measure out? This is a very practical problem. This sort of question pops up a lot when we are doing lab work, doing any real quantitative chemistry. We often need to make solutions, and they need to be of a certain concentration. All right, so what do we know for sure? Well, we know that, well, we know, I guess, a few things. We know the volume, we know the concentration, and we know that we probably have to find the molar mass of this thing eventually. So specifically to our situation, we're going to need a certain volume. Now, somebody else might need another volume of that molar solution, but Maya needs 0.300 liters, or 300 mils. So we're going to start with that. Now, okay. Oh, actually, you know what? If I see a molar, I should actually rewrite that at 0.14 moles per liter. I think that's important, because that helps me. All right. Now I want to know what the mass of silver nitrate is. Okay. So first I can figure out how many moles of silver nitrate there are. I can use my molarity to convert the volume, 1 liter, to some number of moles of silver nitrate. Great. But that doesn't tell me the mass of silver nitrate. To know the mass, so I'm going to need to find the molar mass of silver nitrate. Okay, so to do that, I'll need to know silver has a molar mass, it's probably pretty heavy, 107.9 grams per mole. I've got a nitrogen in there. Nitrogen has a molar mass of 14.0 grams per mole. And I've got 3 oxygens, 3 times 16.0 grams per mole. Okay, and all that together. Oops, I don't want to multiply them. Plus 3 times 16. 169.9 grams for every mole of silver nitrate. Great. Okay, so that says then that I can convert this number of moles into a number of grams that Maya needs to measure out. I can put my moles on the bottom, 1 mole, and my grams on the top, 169.9 grams, so that my moles and my liters cancel out. I'm left with some mass, some number of grams of silver nitrate. 0.3 times 0.14 times 169.9, which is in my calculator, so I'm just going to press the answer button because it's saved. And what do I get? 7.1358 grams. We only have 2 sig figs here, so we're going to call that 7.1 grams of silver nitrate. All right, so next we'll take a look at some Coca-Cola. All right, what do we know here? It's got carbon dioxide in it, we know that. An unopened can of Coke has a concentration of 0.14 molar of carbon dioxide. And I've been stressing, I think it's really important to rewrite any time you have a capital M, to rewrite it as a mole for every liter to help us with the translation. That's what the capital M means, moles per liter. The question is, how many molecules are there in 355 mils of Coke? Did I say molecules of carbon dioxide, I should say, if I didn't say that already. All right, cool. So we're going to start with, what should we start with? Well, start with the thing that's specific to our example. We're talking about a 355 mil can. So we'll begin there. So we got a 355 mils. Now, this is in moles per liter, so we should probably turn this into liters. And I know that 1,000 milliliters is the same thing as a liter. Okay. And what am I looking for? The number of molecules of CO2. All right, so to do that, I'll probably need the number of moles. And I can use my my molarity to convert it from liters into moles, because I've got 0.14 moles of CO2 for every 1 liter of solution. All right, but I'm actually not looking for the number of moles. I'm looking for the number of molecules. So how do I convert between moles and molecules? Well, I'm going to use Avogadro's number. I know that for 1 mole of CO2, I have 6.02 times 10 to the 23 molecules of CO2. So moles cancel, I end up with molecules, and so I can finish up here by saying, all right, that's 355 times 0.14 times 6.0, no, gosh, 6.02 to the power of 23 times 10 to the power of 23, I should say, and divide that by 1,000. All right, so a lot of molecules, which you've probably reasoned. All right, so that's, how many sig figs? 2 sig figs, it looks like, so I'm going to round that to 3.0 times 10 to the 22 molecules. Oops. Okay. Moving on. All right. So let's take a look at Logan's chemical sludge situation here. All right. So this is a thing people do. They make it their business to isolate or to acquire sludge from industrial plants and then go through a process of re-isolating certain valuable ions into metals. Now, these concentrations are probably a little high, probably wouldn't happen quite this high, and it probably wouldn't be gold and silver, probably maybe slightly less valuable ions, but we'll proceed as that's not a big deal. Okay, so what do we got? We got Logan, he gets 12.5 liters of chemical sludge. And the sludge has a 0.15 molar gold concentration, which of course means 0.015 moles for every 1 liter, and 0.0023 molar silver concentration, which we should rewrite as 0.0023 moles for every 1 liter. All right, and the question says, okay, if properly isolated, what is the mass of gold Logan can theoretically yield? Okay, so let's say, well, we'll start, what do we have specific here? Well, we have 12.5 liters of sludge, and let's start with the gold. So we'll start with A. So we start with 12.5 liters, and we can convert that into the number of moles of gold, which isn't the same as the mass of gold, but we always want to convert from mole to moles if we can. So we got 0.015 moles, and that's for every 1 liter. And lastly, we want to convert from moles into the mass of gold. To do that, we're going to use molar mass. Molar mass of gold is 197 grams for every mole. So we have 1 mole on the bottom and 197 grams on the top. Moles cancel out. And then we have a pretty simple calculation here. 12.5 times 0.015 times 197. And I get 36.9. How many sig figs? 2 sig figs. So 37 grams of gold. Okay. Now our silver calculation is going to be very similar, so I'm actually not going to go through a big fuss of talking through my logic here. I'm just going to write it out. Same thing really, 0.023 moles for every 1 liter. And that's times the molar mass of silver, which is 107.9 grams for every 1 mole. And I'm actually going to be real lazy here. I'm not even going to retype this entirely. I'm just going to change the gold to silver. And I get, did I get that right? No, because I also have to change the concentration here. So I'm going to insert my value of 0. And now I want to move back to 2, 3. Huh, okay. Let's try that. 3.1. 3.1 grams of silver. Okay. So on to question 23. All right, so 23 question talks about airbags. And airbags are pretty interesting chemically. We know that we get some sodium azide, pretty reactive compound, green for given. And in a car accident, it rapidly decomposes and it forms sodium metal. And it'll produce enough nitrogen gas to fill an airbag in the process. Which is interesting because it means you may know sodium metal is quite explosive. And so if it is raining during a bad car accident, I've actually always wondered what happens to the sodium that's left over if a car is badly damaged. Is there just sodium metal sitting there? So I'm quite curious. At any rate, so what do we ask for? We ask for what is the mass of solid sodium produced if the airbag contained 7 grams of sodium azide. Okay. So here we see we are going to be converting from one substance to another. So in our work, I think it's going to be really important for us to label which quantity we're talking about anytime. We're talking about sodium azide or we're talking about sodium. So let's begin. We know we have 7 grams of sodium azide. All right. Now, you probably know that in order to get anywhere, we need to convert into moles. So let's start with finding the molar mass of sodium azide. So for the sodium, that's 23.0 grams per mole. And I have 3 nitrogens, so that's 3 times 14.0 grams per mole. And overall, sodium azide is going to be 23 plus 3 times 14, 65 grams per mole. I need to hydrate here. All right, and that will allow us to convert some number of grams of sodium azide to some number of moles. All right, so we'll say grams go on the bottom, so they cancel out. 65.0 grams of sodium azide for every 1 mole of sodium azide. Grams cancel out. I find number of moles. Oh, I should be writing sodium azide in here, like I was just saying I should. Old habits die hard. Okay, cool. Now, we don't want to know about the number of moles of sodium azide. We want to know about how much solid sodium is produced. Probably because when I wrote this, I was wondering about how much solid sodium is around to explode in a rainstorm in a badly damaged car. So, what do we see here? We see that for every 2 moles of sodium azide consumed in this reaction, 2 moles of sodium metal are produced. So it's a 2 to 2 ratio. And so, if I want to convert from moles of NaN3, sodium azide, I know that 2 moles of NaN3 will produce 2 moles of sodium. And that's all well and good, but we were asked to find the mass of solid sodium, so the last thing we need to do is convert from the moles of sodium to the grams of sodium. Now we already found the molar mass of sodium, so we can do this pretty easily. It's just 23.0 grams sodium for every 1 mole of sodium. So let's just check. Moles of sodium cancel diagonally, moles of sodium azide cancel diagonally, and grams of sodium azide cancel diagonally. All right. This should give us a mass in grams of sodium. Let's just check here. So we get 7 times 2 times 23, and we divide that all by 65, and we divide it by 2. And we get 32.5 grams of sodium, which is fairly significant mass. Wait, hang on a second. That can't be right, can it? How can there be more mass of sodium produced than there was sodium azide to be consumed? Oh, I see. I just divided 65 by 2 in my calculator. So let's see if we can try that again. 7 times 2 times 23 divided by 65 divided by 2. And there we go. How many sig figs? Well, I got 7. It's only 1 sig fig, so I'm going to call that 2 grams sodium, which is a little bit less severe mass of sodium. All right. So we did question 24 in class, but I think I'm going to go over it a little bit here as well. Actually, you know what? I think I'm going to call the video, and I'll start the next one tomorrow.